And you can quantify this. So in computational complexity theory, the way you quantify this, as I said earlier, is you have, as time passes, you have some process that's doing some computation. And what you do is, you imagine how many of these quantum gates, or how many of these gates or computational elements do you need to put in to mix the elements in different ways and, move the information around. That's what you would do in computer science. So in physics, you could think about time evolution as a quantum computation. So you remember I was saying earlier that the way you talk in quantum mechanics is the state of the system, and there's a rule that says how the state of the system transforms from one time to another time. That rule is, for the professionals, the action of something called a unitary transformation on the system, and this unitary transformation is determined by the physical laws. So the physical laws, all the forces you have, and what have you, how the particles interact, and that's prescribed for you by the laws of nature, and they prescribe for you how things change in time. So if you imagine the space of all possible unitary transformations, so this is the space of all possible transformations of the system as time passes, the actual system, the actual physical system, follows some trajectory. So this is the transformation. This black line, it's the transformation executed by the actual physical system. So I'm thinking but I'm talking about it as if I was a computer scientist. So imagine the possible transformations of the state. That's like looking at all the bits in the beginning. That's the physical bits of the universe, of the space and the time. And then I imagine transforming them by the application of little, transistors and what have you. See, these are supposed to be the little gates transforming the information. And all of those things are the little physical interactions occurring at each point in space. So you imagine it generates this trajectory. And you can ask a question about how complex this is by considering the geometry of the space of all possible transformations you could have made between states. And then asking, were there any shortcuts to go between here and here? It was an easier way, in some sense, to do this with fewer steps and so on. And complexity of the transformation grows if there are no shortcuts that you could have taken through this. So this is a very, very computer science way of thinking about what the physical processes are.
So there's a question which now arises the third time. I had it in basically your first slide, which has to do with this notion of locality. So if you assume, like Leibniz assumed that space is constituted by the compresence of minimum two things, and an extension, basically your ruler, is already a secondary thing. So the question is this something, now you seem to make a similar distinction between simple and complex, and ironically use the word complicated at the same time. So where you say smaller than K, simple locality rules, continuous space, larger, I don't know. So can you explain, is there a difference? Is there a moment when we actually have something like a kind of relational topological space going on and your ruler goes away, basically?
Yeah. So I would like to be able to say yes as an answer to that question. That would be nice and clean, but I can't, because we don't yet, I would say, we haven't completely nailed what is going on. Right. So at some level, that when you get down to the really microscopic Planck scale fluctuations of the universe, etc. So you have a space that's supposed to be continuous. If it rips itself here, because that's a quantum fluctuation, then these 2 points are no longer next to each other. So it's not entirely clear what you meant by they were local to each other, because they're not next to each other anymore. So you see, so there's clearly something going on there. But I'm actually going to try to talk about something even more complicated. I'm sorry, I'm using the words. There's a limitation of the language of, which is that we're going to get towards the idea that the way these things are actually stitched together to define some notion of continuity is by their quantum mechanical entanglement that's going to arrive at the very end. And that therefore the relation between them can be modified as the degree of entanglement between them changes. So the degree and structure of the entanglement between them changes. So you can have things that are local to each other and then stop being local to each other, and then are local to each other again, depending on the structure of the entanglement. And then it can happen because of a property called monogamy of entanglement, that if these two things are entangled, these two sort of bits of space, if you like, are entangled, so they're kind of connected with each other, And then you have a third bit of space that for some reason, through some process, becomes very entangled with, this first region A. This region A can disentangle from B. That can happen. And the reason it can happen is because they're not entangled the right way anymore. At least that's the current understanding that we're working towards. So then these relations that define locality can keep changing in this way. But it takes very particular situations to produce these effects, because the amount of entanglement has to be huge and has to be structured in the right way. And certainly at the moment, the only way we know of processes that generate these kinds of changes involve gravitational processes and things like, black hole, Hawking radiation, things like this, which is why I'm talking about those examples.
So the question is, you have put in the slide a diagram that looks like a bunch of quantum gates.
Yes.
From quantum computing. And earlier in another slide, you had put a so-called word, a sequence of operators that were acting on the vacuum state. Were those operators quantum gates? Are they the same thing? And then the complexity of that word would be the complexity of the circuit. Am I interpreting it right?
This is an excellent question. And I was trying to slide two slightly different things past you at the same time, and you've called me on it. So here, I'm talking about the time evolution process that takes me from my initial state to the final state. There, I was talking about this combination of operations, which you could think of as quantum gates, as being the thing that makes that final state. The question is, the initial state wasn't those particular operations on the vacuum. The initial state could have been one operator, call it, let's say, the thing that makes a hydrogen atom of a given mass and momentum, and then I apply that one operator a bazillion times, and that makes my initial state. So that's a very particular initial state. And then this time evolution, either this process visualized geometrically as an evolution on the unitary group, or this process visualized quantum computation, is supposed to transform me from that initial state, which is very simple, one operator applied many, many times, to that very complicated final state, which involves a huge diversity of these things played out as a sort of random looking operator.
Oh, so the state space is made of these operators applied to the vacuum state.
Correct. So more formally, the physical system is described by what's called a Hilbert space, which is some kind of vector space with a norm on it that describes all physical states. And then you talk about things you can do to the space as operators that change the vector in the Hilbert space, and the different vectors of the different physical states. So that's the language of the operator-based language of thinking about what quantum mechanics is as a thing. Anyway, there's these are basically hot off the press type of findings. Like this is like a year old or so. These things. So people have now shown that. I think it's important to be very clear about how these calculations are done. So the real astrophysical black holes in 4 dimensions are beyond our capacity at the moment to compute in. So the way in which you study all of these things is you build impoverished models of the systems that you believe capture the essential physics. They're often called toy models in physics. So there are lower dimensional models of gravity with limited kinds of matter in them and not the full richness that we see in the world. In such systems, we've been able to calculate these kinds of things precisely. Okay, and the expectation is, for reasons that we believe that the toy models have captured the essential features of the more complicated systems, we believe this will extrapolate. So just putting the cards on the table. So up to that caveat, to explain the physics of black holes, we expect a linear growth in the complexity of the quantum state over time. So you start with the initial state, which is lots of, the same molecule placed a bazillion times in the system. And you're expecting the natural time evolution through the natural Hamiltonian, through the natural time development of the system to make the complexity in the senses that are described to grow linearly for an exponential period of time. And there's a conjecture that chaotic theories, any quantum chaotic theory, will show this growth. And in fact, there is now evidence showing that this is the case. So in Simple models of black holes, as I said, with the caveats I stated earlier, the shortcuts that would make this complexity not grow are absent. And in this way, in the requisite necessary amount of time, the simple initial states can evolve into these kinds of simple, by simple initial states, I mean sort of, the usual kinds of matter kind of floating around in the world. They can evolve. There's enough time. They're able, you can generate the complexity to make them evolve into very complex black hole microstates. Okay, at this level of models that people have been able to describe. So I'll put that on the table. So the next thing, let me just summarize. I've said many, many things, and these are really at the edge of the state of the art. So I just want to summarize what I've said so far. And then I'm going to sort of do the wrap-up piece, which is itself like about 15 minutes long. So far, I told you the following things. I told you black holes trap information. Hawking radiation seems to erase that information. But if you read the state of the black hole from infinity, if you have enough time, well, if you examine the black hole from infinity, from far away, if you have enough time, you should be able to read the state of the black hole. So information cannot actually be erased, contradicting point 2. The resolution proposed was that black hole states are algorithmically complex. So, well, it's a question of how much time do you need. If you need more time in the age of the universe in any practical sense, this thing is gone, right? And then I argued to you that the evidence as available from various toy models of black holes that we've been able to calculate in is that the underlying dynamics producing these states is chaotic and increases in complexity for the amount of time necessary to produce these kinds of complex states. Okay? So the bottom line from all of this is the argument I've tried to make is somehow the causal disconnection of the black hole interior from the rest of the universe and its apparent erasure of the information is a classical artifact of the algorithmic complexity of its quantum states. So you do coarse classical measurements, and it makes it look like this part of the universe is kind of disconnected from everything else because you just can't get to the stuff because it's so complicated. That's the kind of argument I tried to make. But now we actually have a fly in this ointment, which is we also said that, when I described Hawking radiation, the stuff that actually makes the black hole look as though it's evaporating and erasing the information, I said it actually looks pretty simple. I said, you pair produce a couple of particles, one falls in, one falls out. Oh, that's just a particle, like the particles that fell in to make the black hole in the first place. So if my statement was correct, if Hawking's calculation was correct, it's just a lot of well-separated particles, pretty simple, streaming away from the black hole. So where and how is the information about this original complex microstate stored? So you go with elephants, encyclopedias, whatever, and they become very, very complicated, making this sort of weird old thing called a black hole. It's very hard to decode, etc. And then all of a sudden it's re-encoded over a period of time in this very simple looking Hawking radiation that comes out to infinity. So we can ask the question, in that Hawking radiation, where is the interior of the system encoded? Where is this microstate encoded? Okay. So that has been an exceedingly exciting set of developments that people have been thinking about in string theory in the last 2 years. Very, very exciting time. This is ongoing, so we're sort of don't take anything I say as definitive, right? We're some way along the development, and interesting things are happening.